Hello again, welcome to day 2. This is the second video I'm making on the topic of model with vectors, which is applications of vectors. So word problems only. Also keep in mind any vector can be represented in I and j terms using the formula right here. So we've already covered the first 3 examples. I'll take you to the 4th one. All right. Alexis and Christian are pulling on ropes attached around the neck of a donkey. Here's my donkey. That does not want to move. So of course we're hoping that we're keeping this all safe. We're not hurting the donkey. So it's tied up around this on his neck. Alexis pulls with a force of 75 pounds. Doesn't matter which way I put Alexis, but here's Alexis' vector because she's pulling with a certain force at a certain angle of 75 pounds. Christian wants to pull with a force of 50 pounds, and if the angle between the ropes is 75, so now I know the angle between them is 75. So here's kind of like the triangle. This about this sounds good for Christian's vector. And this is Alexis, and he's using a 50-pound force. The angle between them is 75. What are they asking me to find? Find the angle between the resultant and the larger force. Well, first of all, Alexis' force is larger force, so that makes sense. But then the angle between the larger force and the resultant force. So if you notice, I have 2 vectors here, a 75-pound vector and a 50-pound vector. To be able to find the resultant force, I have to complete the parallelogram and put the equivalent vectors on either side. So if that's 50, that's 50, and that's 75. So I'm going to use the first vector, 75, the Alexis vector, add to it Christian's vector, and the resultant vector is from start to finish. This black vector represents the sum of Alexis plus Christian's, and we can call it vector R as resultant vector. This will justify the addition because we can only have a vector, the tail and the head, and the next vector has to have its tail and head. The tail head. It can only be tail head and tail head. It cannot be tail tail. So tail head. Can't be tail tail head head. Keep that in mind. So to be able to find the angle between the larger force and the resultant vector, I have to first find resultant vector. So let me go ahead and finish that. There's 75 pounds. And here's the 50-pound Christian. Now, the resultant is from start to finish. Just this one here. Let's make it a little thicker. Now, since I have to find this angle, I'm going to stick to that triangle. If you look at the left triangle, that's an SAS type of triangle because we know side. Well, we don't know this angle. Let's see if we can find it, and then we have another side. I have accidentally listed it as a degree, so let me fix that. 50 pounds. So side, angle, side. If that's the case, then I should be able to use law of cosine to find this resultant vector. So the exact opposite side. Let's see if I can find that angle. In a parallelogram, if this is a 75-degree angle, the one opposite to it is also 75. So if that's 75, this one's also 75. And they add up to 360 degrees, which automatically puts these two at 105, 105. Because 75 plus 75 is 150. And 360 minus 150 would be 210. And then divide that by 2 because they're both going to be equals 105. So I technically do know that angle in between. It's a 105-degree angle. So I'm going to use law of cosine to find the resultant vector. Basically, I'm automatically finding its magnitude. Sum of the square of the two sides minus 2 times. Plug that straight into calculator and we should have the magnitude. Let's see. Turns out to be about 100.33 pounds. So the actual force that's acting on the donkey, hopefully without hurting the donkey, is 100.33 in the direction of the resultant vector. This is 100.33. And if I still stick to the same triangle, step 2 would be to find that angle, but I should be able to use law of sine there. The sine of 105 over its opposite side, which I just found, must equal sine of theta over its opposite side, which is 50 degrees. So theta would be equal to sine inverse of 50 times sine of 105. Okay, plug that in, and that angle should turn out to be about 28.78-ish degrees, and that's going to be that angle right there, the angle between the resultant vector and the larger side. Hope that helps. And one last one is a state of equilibrium. So before I start on this question, it says an object is in a state of equilibrium. What that means is all the forces acting on the object, the sum of all those forces will equal 0, which means there's no moment, no rotation, no translation. It's a stable object, which means it's balancing out all the forces acting on it. Like if you look at this example here, this is where all the forces come together. You want to call this, that's force 1. Here's another force, force 2. Believe it or not, there's a third force, which is the weight of this object, F3, which is pointing straight down towards the center of the gravity. So at this point, we have 3 forces acting up. If it's an equilibrium, F1 plus F2 plus F3 will equal 0. We can also say that the sum of all the horizontal components, the sum of all of the x component of the forces will equal 0, and sum of all the y component of the force will also equal 0. And hence, let's try to use this. A box of supplies that weighs 1,200 pounds, so clearly this one, is suspended by 2 cables attached to the ceiling as shown in the figure. What are the tensions in the 2 cords? Which also means what's the forces acting on the 2 cords? Because they're tied up, that force is equivalent to tension. Okay, so if I were to convert this, this is the point where the 3 forces are acting on it. So if I were to call this x-axis, that point is where all the forces come together. Here's F1, here's F2, and here's F3. Now F3 is the easiest one because F3 does not have any horizontal component. It just has south-facing component, and hence force 3 can be written as negative 1200J. Now force 1, if this angle is 45, this angle automatically is 45. So this angle made by force 1 is 45 degrees with the positive x-axis. And the angle made by force 2 is a 150 degree angle with the positive x-axis. You've got to be careful with the second one. Let me go ahead and write all these forces in I and J terms, and then we'll add the horizontal and vertical, set them equal to 0 because this is in state of equilibrium. So F2 would be its magnitude. But please know we don't know its magnitude. Be cosine of the angle I plus, again, F2 sine of the angle J. Now we don't know F2, so F2 is going to stay as F2. That's what we're trying to find. Cosine of 150 is negative root 3 over 2, to get I with it. Sine 150 is half, J with it. Let me rewrite it in a better format here. F2 will be negative root 3 over 2, F2I. Just bring the constants before the unknowns, J, just like how we do in X and Y's. So here's F2, here's F1, here's F2 written as a vector, I and J. Let's also write F3. Sorry, we already wrote F3. We'll write F1. 45 degree angle. So F1 cosine 45I plus F1 sine 45j root 2 over 2 f1 is magnitude I plus root 2 over 2, stick a j with it. It's substituted by its values, right? So that's f1, and here's the third vector. Now, since they're all in state of equilibrium, like I said, f1 plus f2 plus f3 must equal 0, which means its horizontal components must add up to 0, and the vertical should also add up to 0. Okay, let's do that. Horizontal of f1 is root 2 over 2 plus horizontal of f2. It's actually negative, so I'm going to change that sign to here. 2 of f2. And f3 has no horizontal component, so just those two must add to 0. And with vertical, plus vertical of f2 plus vertical of f3 must equal 0. Okay, this is two equations, two variables. I'm going to add the second term to both sides, f2. And then the other one, I'm going to add 1200 to both sides. Okay, now we have two equations, two variables. I could use a substitution, elimination. I'm going to use substitution. If you notice how f1, root 2 of 2 of f1 is the same as root 3 over 2 of f2 force. So here, instead of using root 2 over 2 of f1, I'm going to substitute it with this. Okay, one more time, substitution. Root 3 over 2 of f2 plus half of f2 equals 1200. Now I have one equation, one variable. I should be able to solve them. Root 3 plus 1 over 2 of f2 must equal 1200. Divide both sides by root 3 plus 1 over 2. Time to plug this into the calculator. 1200 divided by root 3 plus 1 over 2. So that divided by 2 times 2 actually. 439.23 times 2. This would be around 878.46 pounds of force. And I'm going to use that F2 in here to find F1. So root 2 over 2 F1, root 3 over 2 of F2. Let me just make sure this math was done correctly. Alpha y equal 1 gets you the fraction format. Yeah, 878.46 is correct. Over here, 46. Both sides can be multiplied by 2, so the 2's pretty much cancel. F1, the magnitude of that force, is equal to root 3 divided by root 2 times by this number, 878.46 times root 3 divided by root 2. Force 1 is 1075.89-ish pounds. The two cables, F1 and F2, are holding this much pounds of force or tension. And then the F3, we already know the tension or the force that's exerting, and all these three are in equilibrium of each other. All right, so that takes care of our word problems for this lesson. This was the second one. See you later. Bye.